All right, get ready, because today we're tackling a problem that's a lot trickier than it first appears. Imagine hosting a dinner party, several couples, and you've decided no one can sit next to their partner. Turns out, planning that seating chart gets really mathematical, surprisingly deep history, too. And maybe, just maybe, thinking about this makes you a better problem solver in daily life. Who knows?
It's the Menage problem, yeah. Sounds like a party planning disaster waiting to happen, but it's way deeper than that. We'll be getting into some pretty high-level math today, using sources like the Online Encyclopedia of Integer Sequences, that's OEIS, by the way, and also the Wikipedia article on, well, the Menage problem itself.
Okay, so basics first. Male-female couples, circular table, genders alternate, no partners side by side. Simple enough, right?
If only. Let's say 3 couples. Turns out there are 12 possible arrangements that actually work.
12. Okay, my brain can almost picture that.
But add just one more couple, so 4 total. Suddenly it jumps to 96 valid arrangements.
Whoa, okay. Things escalated quickly. I'm guessing it keeps climbing from there, though, right?
Oh yeah, exponentially. OEIS sequence A059375 tracks these numbers. 5 couples, 3,120 arrangements. 6 couples, 115,200. Gets out of hand fast. And a mathematician, Touchard, he actually came up with a formula for any number of couples.
So a formula exists just like that. Math is neat sometimes. But maybe, to wrap our heads around this, is there like a simplified version of the problem, too?
Thankfully, yes. This is where those famous Menage numbers come in, sequence A0000179. Picture the women are already seated. The challenge is placing the MN so no one's next to their partner.
Okay, so cutting the problem in half, sort of. Are these Menage numbers still, like, crazy huge, though?
They get big, sure, but not as ridiculously fast as the original. Calculating them uses something called the inclusion-exclusion principle. It's like, imagine organizing your bookshelf. Start with all the books, then remove the ones you don't want, then add back any you accidentally took out, systematically narrowing down possibilities.
Starting to see how even a dinner party turns into, like, serious math. But you mentioned graphs earlier, right?
This is where it gets really interesting. The Menage problem connects to other areas of math. We can actually visualize this with a special type of graph, a crown graph.
When I hear graph, I'm thinking lines and dots, not, textbook graphs.
Exactly. Imagine a crown, but instead of jewels, it has dots, or dinner guests. We divide the dots, men and women, 2 groups. Now, in a complete bipartite graph, every dot in one group is connected to every dot in the other group, but tease no connections within a group.
So like crisscrossing lines between the groups, no lines within themselves. Got it.
Now, to make it a crown graph, we remove the lines that would be couples sitting together. What's left, that's our crown. And here's the kicker. Finding a valid seating chart is like tracing a path around this crown, touching every dot only once. Mathematicians call that a Hamiltonian cycle.
So instead of moving people, we're trying to find a path on this crown graph.
Different way to see the same problem. But, important note, counting Hamiltonian cycles isn't exactly the same as the Menage problem itself. Because with the circular table, shifting everyone over one spot technically creates a new arrangement. Even though on the graph, it might look the same.
So the real-world party's got an extra layer, because the starting point matters.
Yeah.
Can't just shift everyone and call it a day.
Precisely. And believe it or not, there's another graph theory way to look at this, using something called matching in bipartite graphs. It's a bit more technical, but the fact there are multiple ways to see this with graphs is fascinating.
2 different graph ways. This Menage problem's full of surprises. But you also mentioned knot theory, and I'm totally lost there.
Hold on tight, because this is where it gets mind-bending. A knot theorist, Peter Guthrie Tate, he found a link between the Menage problem and, well, how we represent knots, using something called Dowker notation.
Knot theory. Like sailor knots. I'm intrigued, but maybe a little scared, too.
Well, these are mathematical knots, closed loops that can be tangled in all sorts of ways. Dowker notation uses numbers to describe the knot structure. You number each point where the strands cross, then use pairs of numbers to show which strands are in each crossing.
So we went from seating charts to, like, tangled up loops. This is deep.
But here's the wild part. Valid pairs of those crossing numbers in Dowker notation. They have the same properties as pairs of people who can't sit together in the Menage problem. They got to be non-consecutive and have different parity, meaning one's odd, the other's even.
Hold on. So the rules for who sits where at dinner also apply to how these knot diagrams are drawn.
That's the mind-blowing part. And because of this connection, Menage numbers help us count certain types of knot diagrams, specifically alternating knots, where the over-under pattern of the strands is consistent.
Wow, we went from dinner parties to graphs to knots. Never would have guessed those were connected.
Shows you how interconnected math is, right? You start with one seemingly simple problem, and it opens these doors to areas you never expected.
This is why I love deep dives. You just never know where they'll lead. But before we go too far down the rabbit hole, let's recap on the Menage problem so far. Started with seating arrangements, discovered these Menage numbers, which took us to graphs, even knots. But there's more to explore.
Indeed. Our sources mention something interesting about just shifting everyone one seat at the same table.
Right, the source says that makes a whole nido-bu arrangement in the Menage problem, mathematically speaking. But does that really make sense in the real world? Would you consider that a different outcome at your dinner party? It's something to think about.
Great point. Maybe our mathematical models don't always line up perfectly with reality, but exploring those differences is part of the fun. And that's exactly what we'll do in the next part of our deep dive.
Back again. I don't know about you, but my head's still spinning from that knot theory stuff. It's wild how a dinner party takes us to such unexpected places, you know?
Perfect example of how math's full of these, hidden connections between ideas, and the Menage problem, well, it's a fantastic guide through that world.
So before we get too lost in the theory, let's come back to those Menage numbers, the ones tracking all those possible seating arrangements.
Right. I've got sequence A059375. That's for the classic problem, no couples together. Then the simplified version, sequence A0000179. The Menage numbers themselves, women already seated.
And those get huge fast. But there's another sequence in the OEIS that I noticed, A000033. It's called coefficients of Menage hit polynomials. Now, that sounds a bit intimidating, even for someone who likes math.
Don't worry, it's not as scary as the name suggests. These Menage polynomials actually offer a pretty elegant way to understand the problem deeper. They use generating functions, which are kind of like a secret code for representing whole sequences of numbers.
So instead of this long list of numbers, we can pack it all into one math expression. That's cool.
Exactly, like having a master key that unlocks a ton of information. And for the Menage problem, the generating function for these polynomials, it reveals some fascinating patterns and relationships hidden within those Menage numbers.
So each term of the polynomial, it's like tied to a specific Menage number. Like each piece of the code tells us about a different dinner party scenario.
Precisely. By studying these polynomials, mathematicians can see all sorts of hidden connections. Really shows how math tools help us see things in a whole new light.
Like putting on special glasses that reveal the patterns in the world. But we haven't even touched on that knot theory connection much yet.
Ah, yes. One of the most surprising parts of this whole thing, it's not just a puzzle. It has implications for how we understand knots.
Still can't get over that, how arranging people at a table can tell us about tangled loops.
Well,
Incredible.
And it's not just a curiosity either. By understanding Menage numbers, mathematicians have made real progress in knot theory.
It's like this dinner party is a gateway to a whole universe of math adventures.
Exactly. Simple questions can lead down incredibly deep paths. But hold on, there's another twist to the Menage problem we haven't explored yet.
Another twist. Okay, I'm listening. More knots.
Not this time. We're going deeper into the original problem. Remember how strict we were? And no couples together.
Yeah, that was the whole point. Keep those lovebirds separated.
Well, what if we relax that a bit? What if, say, just one couple could sit together?
Interesting. Adding a touch of realism, because in real life, sometimes you can't avoid that.
Exactly. And this tiny change opens up a whole new set of math challenges, A&D insights. It's like a secret level in our Menage problem game.
This is why I love math. Always another layer, another puzzle. So what happens when we let one couple break the rules? Does it change the calculations completely?
Adds complexity for sure. But thankfully, mathematicians have figured out ways to handle these variations too. It's not as simple as the original, but math can still guide us.
That's a relief. Well, we might have to throw out all our work. So what kind of new questions can we ask NOW when one couple can sit together?
For one, how does it change the total number of arrangements possible? Does it increase things drastically? Or is it a more subtle effect?
I'm already curious, and we can push this further, right? Like, what if two couples could sit together, or three, and so on?
Catching on quickly. We can create a whole spectrum of Menage problems, each with its own solutions, like turning the original puzzle into a whole family of puzzles.
And each new puzzle helps us understand the underlying math even better. like peeling back layers of an onion, more complex with each layer. But ultimately, it helps us understand the whole onion.
Great way to put it. Shows the beauty of math. Even a simple problem like this leads to profound interconnected insights.
This variation, letting couples sit together sometimes, it brings us closer to real-world dinner parties, right?
Like bridging that gap between perfect math and messy human interaction.
And who knows, maybe by studying this, we'll find strategies for our own tricky seating arrangements.
There you go. Math often has surprising uses in unexpected places. But before we get too carried away with real dinner parties, let's go to the final part of our exploration, see what we discover about these less strict Menage problems.
Back for the final part of our Menage problem deep dive.
Where we've gone from that strict no couples together rule to, well, a slightly more lenient one.
Right, where one couple gets to bend the rules. Like we're admitting that real-world dinner parties, sometimes you just can't avoid it.
Exactly, and that seemingly small change, it adds a whole new level of possibilities and decomplexity, another layer to the puzzle, so to speak.
So how does it change things, letting one couple sit together? Calculations get easier or harder?
Oh, it definitely doesn't make things simpler. Even with this one change, figuring out the valid arrangements gets pretty tricky.
Makes sense. We saw how fast those Menage numbers grew. No couples allowed together. I bet even one couple throws a wrench in the whole thing.
It really does, but thankfully mathematicians are clever, you know. They've got techniques for this too. Might not be as straightforward, but math can still lead the way.
That's good to hear. Thought we might have to start over from scratch. So, what new W questions can we ask now when one couple is allowed to sit next to each other?
Well, for starters, how does it affect the total number of arrangements? Big increase. Subtle effect.
I'm curious already, and I bet we can take this further, right? What about TW couples allowed together? 3, and so on.
You got it. We can create a whole spectrum of Menage problems, each with its own solutions. It's like the original puzzle becomes like a whole family of puzzles.
And each new puzzle, it helps us understand the underlying math even better, right?
Precisely.
It's like, I don't know, peeling back layers of an onion. Each layer is more complex, but it all helps us understand the whole onion in the end.
Great analogy, and that's the beauty of math. Even something simple like arranging guests leads to these deep interconnected insights.
This version, letting couples sit together, it does feel more like real dinner parties, you know?
Definitely bridges the gap between perfect math and well, messy human behavior.
Who knows, maybe by studying this, we'll figure out how to handle our own seating chart dilemmas someday.
That's the thing about math. It often pops up in unexpected places.
So as we wrap up our Menage problem deep dive, any key takeaways for our listeners? What did we learn?
I'd say the biggest takeaway is that math is full of unexpected connections. We went from seating arrangements to graph theory, not theory, even those generating functions.
It's like math isn't just separate formulas, right? It's this huge web of ideas all linked together.
Exactly. And the Menage problem shows how powerful abstraction is in math. Take a real thing, turn it into math objects, suddenly you understand its structure, explore new variations.
Like building a math model of the dinner party. So we can test different rules and situations.
And by doing that, we get insights that go beyond just this problem, often applicable to other math areas, even real-life stuff.
That's what makes math so cool. But before we go, one last thought for our listeners to chew on.
Go ahead.
We've done the math side of this, but what about the social side? Seating arrangements, they're often tied to culture, customs, all that.
You're right. It makes you wonder, why we do those things. Why alternate genders at a table? What does it say about us when we keep couples apart?
Goes beyond math, but it's worth thinking about. Maybe the Menage problem. It's not JDC puzzle. It can spark conversations about etiquette, social rules.
Seems even a simple dinner party can be pretty deep, both mathematically and socially.
Well said. And on that note, we'll leave our listeners with those final thoughts. Thanks for joining us for this deep dive into the fascinating world of the Menage problem.